Good afternoon, welcome back to the National Space Conference. We are now commencing with the second session, which is the technical session. When I was outside, somebody asked me if they needed a visa to get to Cape Town. And then I was listening to Mr. Brian Dean's speech. One of the things that he mentioned was that we needed to increase and encourage human presence in the space. And I thought to myself, a visa to Cape Town, our space, no, we need to build a wall. So, and then I realized building a wall is not going to help, it's space, so we must draw a line and say only those with visas. Thank you. Standing before you once again is your honored MC Major, Lindy Mwenze from South African Air Force. It is my honor to introduce the second session, the technical session for the day. It is about sharing achievements and use cases for space innovation and services. The moderator for today, I would like to introduce to you Ms. Tanisha Chetty. She is the NEOS Community of Practice co-chair in Circular Economy and Natural Resource Management. Ladies and gentlemen, may we welcome our moderator, Ms. Tanisha Chetty.
Thank you very much. You know, when I was little, I always wanted to be a pilot for the Air Force. And then, because my dad was a detective in the railways, and so that uniform always was very special to me. So I'm truly honored to be addressing such a diverse crowd here today. Good day, ladies and gentlemen, honored guests, our delegates. As introduced, I'm Tanisha Chetty. I thank NEOS for giving me the PhD before it's completed. I'm still busy working on that. I am the academic coordinator for the hydrology program at the University of KwaZulu-Natal, so Sawubona. I'm also the operations manager at the Center for Water Resources Research at the University of KwaZulu-Natal, and I'm so proud to say that we have been the NSTF Award winners for this year for research excellence and human capacity development in training postgraduate students at UKZN. And most of all, I'm truly honored to be part of NEOS and part of the communities of practice as a co-chair in circular economy and natural resources management. Now, this session is called, and if I look here, it says, Sharing Achievement and Uses, Cases for Space Innovation and Services. How does this link up to hydrology? Well, on a daily basis, I'm using hydrological models. If I'm not using it, I'm teaching somebody how to use it. And one of the greatest challenges that we have is that we do not have enough data. So what do? I look up to the skies. All right, so we are using satellite information to drive our hydrological models for rainfall data, evaporation data, temperature data, and obviously land use. We're doing everything from soil moisture estimation to groundwater estimation, etc., just because we don't have enough observation networks in enough data. And for those of you who are from SOARS, I'm so sorry to say it, you are far too expensive for research. So, yeah, data. And the reality is that we have to look at the space technologies, Earth observations, etc., for us to use this data in ways that we can advance our technology. So I'm very proud to host the session and moderate it, and I call upon our first speaker, Ms. Mpho Siddiqui. She's an Earth observation data scientist from Digital Earth Africa, and she's going to be talking to us about mapping water bodies and wetlands in their platform. Thank you. You've got 10 minutes.
Thank you. I hope I didn't just disappear behind this podium. Thank you very much for having me today. My name is Mpho Sadiki, and I'm an Earth Observation Data Scientist at Digital Earth Africa. And today, I'm not here to reinvent the wheel, so just, I'm not going to give you new methodologies of how to map and monitor water bodies, but rather, I'm going to try and make Earth observations a bit easier for you. Sort of think of it as me greasing the wheel a little bit so that you have more time on your hands to do more things with Earth observations. So first, I'll start by introducing Digital Earth Africa. So we're an organization or a program that is continental, but we're based at the South African National Space Agency, so we're literally just next door. And we have a very basic mission. We just want to provide a routine, reliable, and operational service that uses Earth observation data to deliver decision-ready products that will enable different stakeholders to to address social, environmental, and economic changes on the continent and develop an ecosystem for innovation across different sectors. And in order to do that, we operate under key principles, which are that we want all of our data to be free and open to all of our users, and we try and make it continental. So everything that we do, we cater to the entire continent. And we're accountable and we're transparent with everything that we do. We even reveal all of our code. You can get it online and use it for whatever reason you'd like to use it for, as well as diversity and inclusion. So this is a very important part to us, be it geographic diversity, gender diversity. We do consider that in our overall mission. And the main thematic areas that we look at are land degradation, coastline changes, urbanization, water resources and flood risks, as well as, of course, agriculture and food security. I apologize if I'm going too fast, but I only have 10 minutes, so I have a lot to get through. So with Digital Earth Africa, we actually have the largest global open data cube implementation. We have over 3.5 petabytes of data that we host on the Amazon Web Services. And this is thanks to the, let me just get that word right, to the Amazon Sustainability Data Initiative. So that's how we're able to host this large data set that we're able to make freely available to anyone on the continent. So we're also free, even for commercial use, be it, we don't really care what you use it for, we just want to make Earth observations accessible to everyone. And as I said, we have complete visibility from the data to the final product, and we have different interfaces which I will cover for different needs. And we have an extensive library of SDG-oriented tools, and we also have free learning platforms and a help desk to assist you if you are interested in getting into the Digital Earth Africa platform. So here, this is just a snapshot of some of the data sets and services that we do offer. You see that we have satellite imagery, we have products that relate to land and water, we have elevation data, we also have external data sets that, although are not on our data cube, we do provide avenues for you to access them and bring into our platform and include those into your analysis as well. So how do you access our data? We have different options. The first one is the Digital Earth Africa map. This is a website, so it's a map-based interaction that you can use to interact with the different, all the products and services that I just mentioned. You can find them through this website, and you can explore and see where we have coverage, where we don't have coverage, and just have a basic visualization of what the product can offer to you. You don't need any experience in Earth observation. You just need internet, and you can scroll around, zoom in, pan around, and you'll be fine. We also have our very own sandbox environment. So the sandbox environment is a cloud-based computational platform that we provide through the Jupyter Lab environment. We give you free, although limited, compute resources, and it's perfect for technical users who want to explore our products even more. So through this platform, you have access to the entire data cube that we host on AWS, and you can use it to create ad hoc reports, develop new algorithms, as well as do continuous analysis of the environment. We also have a notebook repository. So for the sandbox, because it's a Jupyter Lab environment, we use Python scripting. All the notebooks that we've ever created, that we've ever collaborated with our users on, they're hosted on the repository. You can access it on GitHub, free, you can download it, do whatever you'd like to do with it, and this is also compatible with the Sandbox. So when you do register for a Sandbox account, you do have access to the wealth of notebooks that we have already available. We have over 100 open notebooks that cover a variety of topics and support different SDG indicators. So if you do go there, you will see a lot. We also have other access points. We have our Digital Earth Africa Metadata Explorer. So this is a website that uses the existing data cube to inspect the metadata of all the data that we have available on our platform. We also have the Open Geospatial Consortium web services, so we can deliver our data through those, so you can bring our data sets into more traditional software like QGIS or ArcGIS if this is something you're more comfortable with. Okay, now I'll actually move on to monitoring water using the Digital Earth Africa platform. So first, I'll just like to highlight, these are the imagery that we do provide. So we have the Landsat Collection 2 Level 2 surface reflectance. We also have the Sentinel-2 Level 2A surface reflectance. We also create our own geomedians, which I will talk about, very interesting stuff. And we also have Landsat 2 Level 2 surface temperature, as well as radar backscatter from Sentinel-1 and ALOS from JAXA. So I will highlight these because I want to show you different ways that you can interact with our platform to actually map the water. You can go straight into the imagery, or you can use some of our other subsequent products that I'll go into a little bit later. So with our data, we have what is called analysis-ready data. It's plug and play. It's ready for you. We've removed the pre-processing that you need to do. You just plug it into your application or whatever analysis you're doing, and it's ready to go. So we remove that 80% of the time that we, as Earth observation people, spend on pre-processing our data. So we remove that level of redundancy and allow you to just go into analysis straight away. And like I said, we also have GeoMat composites. These are surface reflectance geomedians and triple median absolute deviation services that provide you composite cloud-free satellite data over specific timeframes. And we offer them at annual, semi-annual, and rolling monthly. So the rolling monthly is actually something we just launched last week, that observations are summarized over a 3-month period starting on the first day of each calendar month, giving a set of new measurements for each month. So you basically have a cloud-free image for your area, for any part of Africa, for each month, starting from 2019 to current. Just to point out as well, our Sentinel archive doesn't go back to 2016, but rather we start at 2017. Now, just to showcase the capabilities that we have, you can do, like I said, I'm not reinventing the wheel. You can do water extent analysis using the modified normalized difference water index. And through our platform, it's so easy. You don't have to pre-process anything. All you have to do is open a notebook, select a study area, and run the notebook, and you will be able to get a timeline of how your water body is changing over time. You can see from this animation, we can see from 2017 to 2023, how the water in that particular example is changing. So we also have what we call the Water Observation from Space product. We're really proud of this one. This was created from the work of Norman Muller from Geoscience Australia and Dr. Dale Roberts from Australian National University. So this is a service that draws on the historical data of the Landsat archive. So it allows you to visualize how water is changing using that archive. So using what we call the WAFs, you can understand the extent of water availability on the surface, which can then be useful for analysis into flood risk assessment, understanding change in water extent, and observing the effects of weather on a certain climate. I mean, this was me trying to explain what it takes into account. It's a decision tree method that is very complicated, but it does take into account, obviously, the Landsat archive, STRM DSM, and it also looks at pixel quality, where it looks at pixel saturation, band contiguity, clouded or cloud shadow, terrain shadow as well as other additional data sets. I won't go into that due to time. So it creates three main bands. You get a WAFS feature layer, which tells you water and non-water classifications, but you also get an annual summary, which gives you the ratio of wet to clear observations for each pixel for each calendar year, and you also get an all-time summary, which is the ratio of wet to clear observation over all time. So this is an example of the WAFs. So it's already pre-calculated, so when you go into the WAFs, you don't have to do anything but select your study area, and you will be able to see how that water body is changing with time. And like I said, we also have the maps where you can go visualize. So this is the WAFs in action. I'm comparing the year 1996 and 2022 for that study area. We also have the Wetland Insight tool. This is a cool tool that provides you with insight into a water body seasonal and interannual dynamics. And it looks into classifying whether it's open water, whether it's just wet, or the percentage of green vegetation, dry vegetation, as well as bare soil. So this is another tool that we offer on our platform that you can use to your advantage. And this is something that you could expect. It will give you, with time, how the water body is changing in terms of the distribution of those few aspects. So I think I'm done, but I would just like to highlight that you can learn more from about Digital Earth Africa. We do have a stand, so you can come to us and we can give you any more information, but you can go to our website for more information as well. And we also have free courses that you can enroll into, and we'll support you for that, all free of charge. That's the best part. Thank you.
Yes, that's how I train them for time. Thank you. That was really quite a beautiful explanation of what you're doing at Digital Earth Africa. Our next speaker is Ms. Tushia Basakwe, and she's going to talk about using the AgriSense constellation as a tool for building sustainable space programs.
Oh, there you go. Okay, so I'm with SES Space. You have heard a lot about SES Space already, so I'm not going to waste time telling you who we are. Professor Mostert, when he was talking this morning, he already mentioned we are into satellite constellations, engineering services, nanosatellites, and hands-on training. So as part of our heritage, he also mentioned that we came from the 1999 year when Sunset Satellite was launched, the first satellite in South Africa, and that expertise and the experience also that went through the Sumandila satellite, we formed SES Space. Over the years until today, we have built 4 satellites in the 100 to 400 kilometer class, and we were using those for satellite engineering training. In 2017, we launched our own satellite, which is the InSight satellite. I'll talk more about that later. We also had development of payloads, and the nice one there, which is the Gecko imager, which was on board the Sunset satellite. But what I want to focus on today is why sustainable space programs. So the country's socio-economic development blueprint encourages us to create a better life for all citizens in an inclusive society. If I may ask you, all South Africans, what is this blueprint that I'm talking about? Fantastic. So, which means it's calling upon each and every one of us to look at the world that you are living in, try and look at the challenges that we are facing and how we can be able to address them. So, which means as South Africa, or each and every one of us, we need to sharpen our innovative edge, and we also need to continue contributing to local and global innovation and technological advancement. Because we can all agree that if we utilize technology, we can be able to address most of the challenges that are facing our society. And I also believe that space technologies are well suited to address some of our societal challenges. And I think over the talks of yesterday and today, we can all agree that that is very true. And here is a slide that talks directly to the benefits of space technologies. So most of the time, if you look at, say, countries in Africa, even maybe us sometimes, when we go and we launch satellites, the very first thing that we're looking at achieving is national pride. Oh, we launched a satellite, we are so proud of ourselves. But there are other things that we really need to look focusing on, like, we have to launch satellites to address a certain challenge or certain challenges that we're faced with. Another benefit is that when we launch these things into space, we develop infrastructure, so space infrastructure, ground infrastructure, and space is also very useful when it comes to creation of high-tech industry, and also in terms of transferable skills to other industries. So it doesn't mean that if you're trained in space, you are locked to be working in the space sector only. Those skills that you gain, you can use them in any other industry, many other industries. So another important thing, there's been a lot of talk about collaboration. So it encourages synergies to be formed between government, industry, and academia. So I've mentioned all these beautiful benefits, but let's look at the situation in South Africa. Because, it's clear, if space technologies are so important, then we should be embracing them and really making a success out of them. But when you look at what happened through the years in South Africa when it comes to launching satellites, we said 1999 we launched Sunset, and then there was Sumbandila 2009, which was 10 years later. And then there were others, Zakub 1, Insight in 2017, and so on. So when you look at the spread of that, you ask yourself, if this thing is so important to help us solve societal challenges, why are we not consistent? Why are we not maintaining the momentum? And I will say there are challenges, and some of those challenges not entirely exclusive to us. Most of the African countries that we talk to also go through similar challenges. You find that there are very unsupportive political decisions and unfavorable agreement structures that we get locked into when we're doing these programs. Sometimes we don't even consider a use, sustainable use of these technologies when we're launching the satellites, and no plan of launching follow-up satellites. Also inadequate training, and because of all those who are trained in this, we end up losing them to other countries because they want to go looking for greener pastures. So I'm actually inviting you, let's eat. Because when you look at the thing that I just laid out now, it's like to tackle it, it's almost like eating an elephant. And the big question that's always asked is, how do we eat an elephant? Are we going to carry it like that and put it on our plate on the table, or do we need another plan? So I want us to look at sustainability elements, which I've identified. This is not all of them here on my list. First of all, we need to look at infrastructure when you go into developing a space program. Human capital development, very important. I also touched on effective utilization of the systems, and also collaboration that is internally between government, academia, and industry, and also government to government. Also, the issue of collaboration, we need to look into that. And the most important one there is continuity. I put a note there for myself and said longevity, which talks to the extent that this thing continues for a very long time. So I'll give you an example. There has been many programs, like I said, in South Africa, where we try to, launch satellites, and they all, continue to some extent. So in SES Space, we launched the Insight satellite as a program. It's a 3-year program, which is funded by the DTIC. And in that, we launched the first satellite in 2017 as part of the QB50 constellation. And I already said it carried the Gecko camera and stuff. So there's an example of a picture that some of the pictures that we got from the satellite, it has descended already. Now, if we look at the sustainability thing that I was talking about, did we meet some of those elements that I mentioned? So in terms of infrastructure, yes, we did have a satellite, and we're gonna build probably launch another one next year and so forth. Human capital, we managed to produce some PhDs and some MNGs and BTech and interns. Effective utilization, well, it wasn't really meant to be utilized for long periods. It's a nano-satellite with a 3-year lifespan. So I would say none, but it was actually meant to collect some data. It was an experimental satellite. In terms of collaboration, massive achievements in the South African space industry. And collaboration, yes, because it was part of an international constellation. And continuity, I would say minimal, because it's only 3 years, which means whatever that you were doing after the 3 years, if you don't continue, then the program dies. I talked about collaboration. That slide there is all the South African partners that were involved on the InSight project. Another important thing for sustainability is commercialization. On that project, we managed to get a number of things that we are able to sell today. So I would say in conclusion, based on what I've just said, so it means that these following factors are very important to consider when you're looking at formulating a space program. Look at your infrastructure that you're putting in, both upstream, downstream, and maintain this infrastructure. There is power in numbers when it comes to human capital development. Look at both theoretical and hands-on training. Effective utilization, you need to research user requirements so that once you launch your satellite, you develop a strong user base so that you have people who are really using the satellite data that you're producing. Collaboration, internal and external, very important. And continuity, here we're looking at repeatability. And a constellation is a very good tool for us to achieve that. So that is why we are now looking at using the insights lessons and experience to build those satellites beyond 3 years and form a constellation that focuses on agricultural applications. And once we do that, then you realize that in terms of sustainability, that program is going to be meeting the different elements that I just mentioned. We have the satellites in space, ground stations, space laboratories, and this, ladies and gentlemen, applies not just only to South Africa, but also to other countries in Africa who are really struggling to get things going. And that is why the importance of collaboration that I mentioned, looking at African countries and really trying to help them to get started and maintain the momentum. Because if they succeed, their success also will mean our success. So in short, I'm saying for us to be able to eat that elephant, let's first identify the different parts, break it up, and eat it piece by piece. Thank you.
Thank you, Tusha. Excellent. That was excellent timing.
Good afternoon, everyone. Welcome to this lunch hour concert. I'm Reinhard Sieberhagen. I'm working at the National Metrology Institute of South Africa. So my talk will be about discussing or just briefly introducing concepts like metrology, measurement, calibration, traceability, uncertainty of measurement. And then I'll give some examples of what we do. So to start off with, NMESA is mandated by the Measurements Unit and Measurement Standards Act, Act 18 of 2006. And I have to read this to apply the International System of Units, the SI, in South Africa and maintain and disseminate the national measurement standards. So at this stage, what is meant by maintain and disseminate is, maintain means you make sure that your measurement standards and procedures are in place and calibrated and you also compare your capability internationally. Disseminate means you pass your traceability on to industry. It's important to note the MISA is one of the DTIC's technical infrastructure institutes, so we report to DTIC. As far as our laboratories are concerned, we have 3 technical laboratories: the chemical material, medical metrology, physical and electrical, and applied. Today we will mostly be interested in the physical and electrical metrology lab. So in this laboratory there are actually 10 sections or sub-labs. I'm specifically from the photometry and radiometry laboratory. Briefly, what is photometry? It's light measurements pertaining to the human visual system. Radiometry is more broader. It involves or includes ultraviolet, visual, and infrared radiation. The picture there, it's called a photometer. Its response is similar to the human eye. So just in case if you're wondering, I didn't drop it and then try to glue it together. That is how it's manufactured. If you're interested in knowing what's going on there, you can ask me afterwards. So National Metrology Institute of South Africa, we know all the words maybe except for metrology. So metrology is the science of measurement. So it will include all the theoretical and practical aspects, your procedures that you use, your techniques, skills, mathematical modeling, statistics. So science of measurement, what is a measurement? It's simple, but let's just say what it is. It's a process of experimentally obtaining one or more values attributed to a quantity. So an example that I show here is that of a mass. So the mass piece, the quantity is known as mass, and it's measured in the unit of kilograms. So let's say I measure this once, and I see that the mass is 1 kilogram. So what is the role of metrology then, more in general terms? It is to link all measurements to the SI units. So you can see the picture there, the 7 SI units there, the diagram. What's interesting to note is just that the kilogram, until quite recently, was the only unit that was still realized or maintained using a physical artifact or a set of physical artifacts. So there are a set of these 1 kilogram standards in Paris, in France, and each country also has a set of these kilogram standards. A comparison or calibration implies someone goes for a trip to Paris to compare your mass piece against the standards in Paris. So secondly, the role of metrology, it's also to ensure international traceability. Now, I've mentioned on the first slide, we do comparisons internationally. So this means that what we measure or what is internationally recognized. So if you measure a can of baked beans and it says 425 grams, it should weigh that same mass or weight all over the world. And then lastly, I talk about an assigned uncertainty. So you need to know what is the uncertainty in your measurement. Okay, briefly, what is the MISA's role in South Africa? To provide calibration and measurement services to the South African industry. And again, it must be traceable to international standards. So what is a calibration? Again, I think it sounds very simple, but let's discuss it quickly. So you compare measurement values produced by a device under test, so that is, or your unit under test, the instrument that you want to calibrate, and you compare that against a known standard or known calibration standard. And it's important, again, if we say it has to be internationally traceable, there has to be agreement on what is a suitable calibration standard for a specific quantity. I show a picture there, it's a vernier. the vernier is used to calibrate, is calibrated against that gauge block, so not the other way around. Oh, okay, almost hurry up. Okay, so what is a standard? The way I interpret the word standard is, it's either a measuring device or system, therefore equipment standards, or one can also view it as documented principles or methods or procedures that you use when you use your equipment. Again, important, if I say international traceability, it means that these standards and the equipment that are identified should also be acknowledged and accepted internationally by experts all across the world. The diagram I show there, that's where we are. CCPR stands for Consultative Committee in Photometry and Radiometry, so it's an international cooperation. CIE stands for Illumination Engineering, Illumination Council International. I'm not going to try and say that in French. And then we are not the only NMI in the world. There are many national metrology institutes, and all of us interact in all different ways. Okay, so calibration relies on two important pillars, traceability and uncertainty. So traceability, simple terms, means you calibrate against, say, a primary standard, then you have something that is calibrated against that, you can calibrate another thing. So there must be a chain linking it back to your primary standard. Uncertainty can be described as the doubt that exists about the result of a measurement. Again, if you wonder why would there be doubt if you measure something, you measure it. Come and talk to me afterwards. Okay, so this equipment, the one in the center, this is a cryogenic radiometer. It's a primary standard used to measure optical power. So you can calibrate other optical sensors against that for optical power. If you look at this, some of you may recognize this as a monochromator. You basically need this and this to give you a spectral responsivity scale. If you're in the industry of calibrating satellite images or drone cameras, you ideally want to measure or calibrate it for spectral responsivity and also for its absolute radiance responsivity. This instrument here, spectroradiometer, is typically used to calibrate the output of an integrating sphere light source, or it's also used for field measurements when you, say, for instance, collect leaf spectra or ground spectra. This is a laser system used with this cryogenic radiometer. Next level, if you want to move away from monochromator and spectroradiometer in your laboratory, you go to a tunable laser system. Okay, this is not meant to scare anyone. This is an uncertainty budget. Sorry. So this column here, there are, in any measurement, there are factors that influence the measurement that you perform. If you're measuring distance, temperature would, for instance, be an issue there. The center part is the statistics used to analyze or treat your measured data, or the influence that one of these sources of uncertainty will have. And there, right at the top, don't know if you can see that, the uncertainty. So this is a wavelength verification of the spectroradiometer that I showed you in the previous page. The uncertainty is 1.227%. Okay. So this innocent-looking graph, it's my last slide. What I depict here is, most of you will recognize this as a leaf reflectance spectra. So I said to myself, if I design an instrument or specify a hyperspectral imager, for instance, 30 or 40 bands. The band width is typically, let's say, 1 nanometer band, full width half maximum. What I did was to select 2 band positions and calculate the band radians in that band. So, why is calibration important? If you assume that your supplier supplied you with a filter at precisely 690 nanometers and precisely 800 nanometers, but it is not at that exact position, what is going to be the effect of what you are measuring? And remember, you don't know it if you don't calibrate it. So what I did was just a calculation. If I shift this peak around with half a nanometer, half percentage, so that would, then the shift in the central wavelength is about 1.7. If I shift the wavelength with 0.5%, the change in band radians is only 1.7%. Now you may think that's small, or maybe it isn't. You have to take into account what you're using this data for, what is your data product. But let's look at this band here. 0.5% shift in central wavelength, the change in band radians is going to be 25%. So if you do not know what the band position is, your data product is not as reliable as you would like to have it. That's all from my side. Thanks.
Good day, everyone. My name is Yeliswa, and today I'll be speaking about mapping weed infestation in maize farms using biomass. So what is maize? Maize is the third major cereal crop grown in the world. It's very important, especially in South Africa, because in sub-Saharan Africa, South Africa is the top maize producer. And unlike the rest of the world, maize in Africa and South Africa is used for human consumption. So I will then speak about my work in the detection of weed species in maize farms. My introduction is that in maize farms, like I've said, I have highlighted the importance of maize production in South Africa. But one of the major obstacles from achieving maximum crop growth and quality is weed infestation. And losses have been estimated in a lot of studies, and some have even reported 90% loss in maize production due to weeds. And these losses are mainly due to the fact that when weeds grow in a maize farm, they tend to compete with the crop. And when they compete with the crop, because of their life cycles, they tend to be able to dominate due to their efficiency in nutrient consumption over the crop. This occurs in the early growth stages of maize. This is when the weeds can remove all of the nutrients from the ground, and so the maize will be affected from that early growth stage. So this then means that to remove weeds, we would need to act during the early growth stage. Farmers have realized this through time, and a lot of techniques have been used, including inspecting farms and scouting. But this is not a temporary reliable because of the fact that weeds grow whenever they want and wherever. They are hard to predict because weed as a term is inclusive of a lot of species which have a lot of growth types and growth cycles. So the role of remote sensing in this is that because we can use imagery and the spectra to delineate, we have been able to use that to detect weed. But before that was done, a lot of challenges were because a lot of weeds are similar to crops, and therefore the ability to use the spectra to delineate weeds from crops was questioned. But through the years, hyperspectral remote sensing has been used. But what it does is that it requires a lot of updating of the data because, as I said, there are different types of weeds that grow. So you would need to upgrade your weed occurrences and your weed types every year if you use hyperspectral remote sensing. But then we have, because of all that information, a lot of researchers had opted to use hyperspectral data, but Sentinel-2 offers a lot of advances in comparison to other satellites, like free source satellites. This is because they offer red edge and they offer a spatial resolution of 10 meters and a 3 to 5 day temporal resolution. Before this year, a research has been done using Sentinel-2 to detect weeds. However, the spectral data is informative and reliable, but it has shown that the high intra-class variability has reflected that the models cannot be generalized, repeatable, and they would require seasonal training, which then defeats the purpose of we would like to detect maize crop, wheat plants in the early growth stages and act on time. So this is what, and when this was realized through research, a lot of models had used vegetation indices, and those have reflected the fact that phenological factors like cover, chlorophyll content, and biomass can also be used to discriminate weed-infested plots of maize farms and non-weed infested plots. The standard practice in maize farms is that maize is planted at the same time, and it's usually of the same cultivar. This therefore means that we would expect the maize to grow at a certain level, and we would expect for the biomass to be at a certain level at each point in time for the whole farm. due to planting at the same time. But then we have seen that weed adds into the biomass of the field, and we then want to see if cover and biomass it can then be used to discriminate weed-infested plots. We used the data from 6 farms around Gauteng and Mpumalanga. So for biomass, we used the leaf area index to proxy for biomass, because we could also go into the field and record biomass using LAI. We then used vegetation indices to try and estimate LAI. This is because they are able to indicate the vegetation greenness, and therefore they are very correlated to LAI. We used the data from Sentinel-2, and the data was rescaled to the 10-meter resolution to create the indices. The data was collected in the field at the early growth stages, which is when the maize is in 6 to 8 leaves, and 57 points were collected. Thresholding was performed, so this is when we said we would use the data to find a point where the a point where there is an average for plots that were not infested. So then we would say that if at this stage of growth we expect this much biomass, anything above that we can then assume to be weeds. We used the random forest classification, and the data was partitioned into a 70-30 training and validation. The accuracy was tested by doing a linear regression between the field data and the predicted data, and then an RMSE was performed. We had 57 points, and the threshold, the point where we saw that this is where, at the early growth stage, this is the biomass we expect of weed-free plots, is where these intersect, and then anything above that is an indication that there's weed in that field. We trained, the training data was tested as well to see how close the model could predict itself, and that was 99.9, and then our tested data, it gave us 97%. And then this indicates that the model and the concepts can then be trusted, but because of the number of ponds that were used, we are awaiting for the next season so that we could find more points in the early growth stage, and that would aid in the robustness of the model, so that we will not fight with the reviewers when we publish. These are my references, and these are my acknowledgements. I'd like to thank the NRF and the farmers, and I would also like to thank the University of Pretoria and then the CSIR.
Thank you. That was actually excellent. We're doing a similar study using drones, and obviously I'm going to talk to you after this. Our next speaker is Mr. Tswelo Pitt. There you are. Okay. Tilly, you're going to introduce your own topic. 10 minutes.
Good afternoon, ladies and gentlemen. My name is Tolopit Mashita. I'm from a company called Abir Innovations, and we do create property identity for rural households and townships, as well as we do livestock tracking and monitoring. We did receive some grants and funding from the likes of TIA under the grassroots program to expand that property identification process, where we made the tourism businesses in townships and rural communities to be visible. We also received the grant from the likes of the IDC under the KEEP program, and also they wanted to expand on the creation or to create property identity for those areas that are not normally found on the conventional navigation and maps. But today, I just want to focus more on the other part of our service, which is livestock tracking and monitoring, which I'm going to be talking about the impact of earth observation in rural communities. So when I grew up, my grandfather was very rich, very, very rich. So he had over 10 cattle. So when he was excited, he would just point at one cattle and say, you know, Christmas, next Christmas we're going to slaughter that one. And we'll slaughter the cattle, and, you know, we'll have the 6 months of meat. We'll do the biltong, you know, we'll do our own natural biltong, and then we'll have the meat for the whole 6 months. But the problem with my grandfather's wealth is it was not monitored and it was not insured. So one morning we woke up and all his wealth was gone, stolen. The whole kraal had to be closed. So someone can ask, what is livestock tracking? So livestock tracking involves the use of technology such as the GPS tracking devices, as well as the RFID tags, in order to monitor the movement and the health of animals, precisely the livestock. And you can ask yourself, why is livestock so important? So to give you an example, yesterday I was talking to Mr. Matsapula. He is over there. He said something very important. He said livestock is like an oil to rural communities, and that's true. So livestock is wealth, it's investment, it's a livelihood to rural households. So just to give you an example, if there's a wedding, normally, culturally, there has to be a cattle that is slaughtered. If there's a funeral, there has to be a cattle that is slaughtered culturally. So it serves a lot of things more than just, you know, the investment and wealth. So it serves as a cultural, you know, significance to our communities. And you can sell livestock to take your kids to school, you can build houses, you can do so much with that. So hence, it's so much important to rural households. And the challenges that has been faced by communities are the likes of livestock theft, which, you know, the NSTF has estimated that around 870 million, but this is back around 2013. But I think now it's over $1 billion, because some of the theft are not even reported. And you've got lack of effective grazing management, animal health. You also have the problem of herd management. And because of these things, and because of the problem that when I grew up, I saw my grandfather losing his head, and, you know, the effect that had on him, because it even affected his health. So we embarked on really finding the solution to this problem. So what we did is we didn't want to start by creating a solution because we think we know what the problem is. So the first thing was, let's develop a system, then use the existing hardware devices like the GPS tracking devices and plug that to the system. And let's do a bigger pilot and understand exactly what the problem is. And we did that. We went to different communities around. We tracked a couple of, you know, livestock from several kraals. And our target was merely not just commercial farmers. We wanted to address the problem of rural households and smallholder farmers, because that's where high theft is happening, because there is no shelter or fence to start with to enclose the animals. So these animals will roam from village to village, you know, from community to community, and it poses a lot of risk. So we did plug our system to the existing GPS tracking devices, and as such, we have identified so many other things, and we listen to our customers. So we plug our system to the device, and our customers can actually be able to, let me go back, they can be able to view the real-time movement of their animals. Just to show here, so this was one of our customers' livestock. So this is the village setup. So you can actually see the level of the battery, the direction, and all the time, and all the necessary information. But this was not enough, because what we wanted to do was to listen to our customers to say, what is it that you actually want? And our customers, they said repeatedly, we want a kraal protection, not just an individual livestock, or not just something that would work for one animal, or take 2 animals, or take 3 animals. What we need a comprehensive kraal protection, because that's what will work for them. So just to expand on that, so this shows the area where most of our customers, as part of the pilot that we did with the GPS tracking devices, were actually are. And we were able to collect a lot of information from these customers. And this is the kraal setup from a rural community. So you'll find this in almost every family. And so this is like in an area of about 50 square kilometers, these customers that we did the bigger pilot with. And so this was just to show an animal in the forest. So our customer could actually have a system, an app on their mobile phone, and they can be able to see the real-time movement of their animals, which direction is going into. This was at a place called Masodi. It's a township close to Mokopane. And from that pilot, there are a lot of things that our team actually wanted to understand, because what we really understood is livestock is affected by so many things. For example, when it's raining, livestock tend to go further from the kraals, and they get more stolen in where like rainy seasons and all that. So we are using this data that we collect, we are using this data that we are collecting from this test and this pilot to actually understand what more can we improve in terms of really understanding what the customer wants. For example, incorporating the weather services, so that if there's a storm coming, then we can be able to inform our customers on time. They can bring them back to the kraal. And if there's a wind, if there's other things that will affect the pattern and the movement of the livestock, we can be able to advise them, not just offering the protection from theft, but also some insights of how to really keep their livestock very protected and safe. So this is where we engage with local communities. This was actually a livestock meeting where the police were present, and we like meetings like this because they give us a lot of insight into actually to understand what the problem is and actually perfecting what we are developing. And like I mentioned, we managed to, with the pilot that we're doing, we managed to get 35 paying customers. And this was just to test if there will be an adoption of our technology in rural communities. And we have over 80 confirmed awaiting orders. And this is just in an area around Mokopane. It's a small area. We receive calls as far as 200 kilometers without doing any comprehensive marketing campaign, people asking us about this service. So we're developing a system called Leshaka Tracking System. This is the system that we're developing based off the feedback of our customers. And we are collaborating with the University of Limpopo, the digital hub in the University of Limpopo, and our partner INCAP from Polokwane to develop that system based on the feedback. It was important for us to understand exactly what the problem is before we can start spending too much money on the hardware and other things, before we could actually pinpoint what the problem is for rural households and smallholder farmers. I think I end here. Thank you so much.
Thank you very much for keeping to our time limit. Our next speaker is Mr. Liam Kogel. Liam's from the ARC, and he's also a PhD student at Stellenbosch University.
Awesome. Good afternoon, guys. Very nice to be here. We're very happy to be here and to present some of the results that have come out of my PhD and some of the field work we've been doing. I'm Liam Sean Kogel. I'm a PhD student. My supervisors is Dr. Alana Rebello and Professor Karen Esler. And my topic is on mapping the presence of invasive alien plants in the Luvuvu catchment using multispectral Sentinel-2 satellite imagery. So just a quick intro before I get into the nitty-gritty of the project. I just want to introduce the MapWaps project, which is a greater WRC-funded project that my study is conducted under. And essentially what MapWaps aims to do is, it's in the name, which is to map woody invasive alien plants and their impacts within strategic water source areas. And you'll see the map on the right there, that the MapWaps project has got 4 focal study sites, being the Tugela in KwaZulu-Natal, the Sabi crocodile catchment in the Mpumalanga, Umzimvubu catchment in the Eastern Cape, and then the Levuvu catchment, which is in that northeastern corner of Limpopo. So yeah, I'll try to keep this short and sweet, but essentially our aims are to use freely available satellite imagery, but also database applications, such as Google Earth Engine as an example, that is freely available. And yeah, just also very briefly, the methods for the greater MapWaps project is essentially to engage with strategic stakeholders to determine, firstly, what are the key invasive alien plant taxa that we should be focusing on, and then secondly, to go out into the field and actually gather data on where these infestations are, and then from there to process data with a Sentinel-2 classification to actually plot out and detect where these infestations are. And yeah, thereafter, just to make all the training data that has been captured available on iNaturalist. So yeah, just quickly, the project team is my 2 supervisors, Alana and Karen, and then it's myself and then Tandeka Skosana, which will be talking just after me. And yeah, just to get into my actual study, so I'm focusing on 2 different catchments. Today I will be presenting the Levuvu catchment in particular. And yeah, you might be asking yourself, why invasive alien plants and why strategic water source areas? Well, invasive alien plants, particularly woody ones, pose serious threats to South Africa, starting with its ecosystems where it can reduce biodiversity, displacing other indigenous bush and other indigenous South African species. It can be detrimental to our economy as well, where it can hinder agricultural productivity, hinder the quality of soils as well. It's just a picture of some Mauritius thorn that is growing literally right over a macadamia tree within an orchard. And yeah, the list can go on and on. They also, certain invasive alien species are known for exuding allelopathic chemicals into the soil, which are quite harmful to the surrounding vegetation. They can increase fire risk as well. So the list really can go on and on as to why this is such a serious threat within South Africa. But what a really important problem is that we're facing in South Africa when it comes to invasive alien plants is that they are consuming significant amounts of water when you compare them to their native counterparts. I've just got a picture of some lantana enjoying the moisture in the area at the Albacini dam wall in the Levuvu catchment. And so, yeah, so the question of why strategic water source areas. Strategic water source areas are those areas that have been delineated strategically and actually only takes up 10% of South Africa's land area, but actually produces about half of our nation's fresh water. So these are very special places across the country. And as I mentioned earlier, invasive alien plants which consume significant amounts of water is a very special and important problem within strategic water source areas. And so we need to manage these invasive alien plants, but to do so, we need to manage them, but we need to measure it. We can't manage anything without measuring it first. And that's where accurate, updatable maps comes into play, which is something that we don't have readily available in the invasive alien plant space. Okay. So just very quickly to go through my methods, I've touched on this, so I won't spend too much time on it, but we hosted virtual stakeholder workshops to determine, firstly, what are the key invasive alien plant taxa of concern? Also, practical considerations. How do we actually get to some of these infestations in the first place, like physically to get the data there? And also just to gain perspective of what the invasive alien plant issues are within these separate catchments, because the issues would be different in each of the catchments. And then, yeah, just going out into the field and having a blast, collecting photographs of these infestations, and these photographs will be geotagged, and that will essentially serve as training data which we'll process later in a Sentinel-2 classification. So yeah, it sounds like easy work just driving around in the bakkie, getting some data, but that wasn't the case. We actually had to drive into some really remote areas, some really treacherous roads that we had to 4x4 on. But yeah, it was a lot of fun. And yeah, then just to say also that this data in the field was captured rather easily on a mobile app that we used, which is called Cyber Tracker. Okay, so now our fieldwork is done. We've got our raw training data. We now process it further in ArcGIS Pro, getting it ready for the actual classification. And that is done with Sentinel-2 multispectral imagery. And yeah, we'll do a series of classifications with strategic bands and indices. And then just for today, with the results I'm showing, I've done an overall accuracy assessment with the confusion matrix. The results I'm going to be presenting is actually hot off the press. We've only come back from the field about 2 weeks ago, so there isn't much more data analysis and stats attached here, but yeah, this is pretty much the starting point. And then yeah, also just to mention that after all of this is done, that the training data will be uploaded to iNaturalist, so that everyone has access to it. And that also, very importantly, that we'll have a online GitHub repository, which is also readily available to anyone, so that whether you are a researcher, a remote sensor, or even just a farmer that is interested in our methods, the data, the coding scripts, everything, that you can access it. And I think this is just very important in South Africa and just for our future development, that across disciplines, that there can be continuous learning and that there can be data transparency and also just that continuous integration. Okay, so just very quickly some results, starting with what was discussed at the virtual stakeholder workshops. So this key on the left is basically the land use land cover classes that was decided we will go out in the field and try to capture. So different agriculture types, orchards, many different orchards, grassland, indigenous bush, that's just some mopani trees over there, water, wetlands, beautiful wetlands in the Luvuvu catchment, and also bare ground and all sorts of other habitat types, including invasive alien plants, which I'll get to in a second. But yeah, before I get into the actual classification, I thought I'll just share some fieldwork observations. I think it's important in order for us to interpret the data analysis and the results that we're getting, to have that context and to paint a picture of what is actually happening in the landscape. So yeah, something that really struck me was just the great dependence on water within the catchment, by communities, by businesses as well. And that, yeah, there was even orchards and certain agricultural activities grown right within natural wetlands, such as this picture here. And also many little community crop fields or crop gardens that were directly irrigated from rivers and dams. And then also, yeah, just many different agricultural types. On the right-hand side, there's some tea and large tea estates, and also just different orchard types as well. So banana, macadamia, pecan, guava, avocado, and mangoes. And yeah, the thought was that, okay, we are in the field and we're seeing that there is these, this distinct agricultural types. So what we did is actually try to run them as their own respective land use land cover classes. So we would have an orchards banana class and we would have an orchards nuts class as an example. Tea was also extracted. And yeah, we found the same thing happening within the indigenous bush. So yeah, I struggled to put all the indigenous bush training data that I found into one big class. I noticed that there is 2 distinct indigenous bush veld types within the catchment. For one, the central southern regions of the catchment where it's a bit wetter, there was a nice heterogeneous bush veld made up of Vachellia, Senegalia, Dicrostachys, Terminalia, aloe, and other species. And then in the more northern arid regions, you would have more homogeneous, more piney bushveld with bits of combretum and other indigenous bush species. Invasive alien plants, there was plenty of those, particularly from the plantations. Obviously, a plantation represents a really large and dense stand. And so for the gum and pines that we were after, we were able to get training data for that quite easily. But yeah, our other more shrubby, smaller invasive alien plants in the catchment were a bit more tricky to capture. This is just another picture or classic example of what we encountered in the field, where you've got very dense bugweed growing, but underneath a canopy of pine. And so therefore, using that as training data just wouldn't be valid. Okay, thanks, I'll be quick. Yeah, and then just to wrap up, that there were also other messy situations where you'll have a combination of 2 or 3, maybe even 4 different invasive alien plants mixed together. And so therefore, to get a very pure pixel of a certain taxa was quite difficult. This is just some more pictures. I won't spend too much time on that. But yeah, just to finish off, my question was, to what level of detail would I have to go to get the best mapping results and to actually effectively separate these different land use, land cover classes encountered in the field? And that brings me to my Sentinel-2 classification. I won't spend too much time on this either, but essentially I, for now, have done 3 different classifications. The first one was where I separated all the invasive alien plants from one another and then ran the algorithm. And then I've got a second classification, which I ran gum and pine separately, but then I thought that maybe to improve the accuracy, I will merge these smaller shrubby invasive alien plants together, given that in the field, they were growing together in a lot of instances. And yeah, and then classification 3 I did where I just merged every single invasive under the sun into one big bin class. So yeah, just very quickly, my final results. This is just what the classification gave me. This is classification 2 that you saw in the prior slide. And just to note that in your northern arid regions, that the classification successfully it showed that the Mopani indigenous bush is restricted to that northern arid region. And that the blue circle there, that all those green colors are representative of in the other indigenous bush and indigenous forest, that is restricted to the wetter regions again. And then, yeah, just that green circle to show that you see that red and orange blotches there on the map. That's your mountainous regions where there are extensive pine and gum plantations. So yeah, just very quickly, I won't spend too much time on this either, but just to say that I did verify with my training data that what is orange here is actually gum, and what is red here is actually pines. And just to quickly bring your attention to this little spot here, which you can see has quite a bit of purple. That was a recently timber harvested area where they just left the fields open. And what happened is you had a lot of bugweeds coming up. So that's what that is actually showing you there. So yeah, just closing remarks to end off. These maps will be really cool for managers on the ground and that wants to apply some mapping at a regional scale, and that we can determine approximate extent of invasive alien plants using this method at a catchment scale. And this is important for prioritizing certain invasive alien plant clearing operations. And also to detect potentially new infestations where we haven't ventured before, where we haven't explored before. And yeah, just a final note that this can be replicated in other strategic water source areas, which I think is quite important going forward for our nation. And yeah, just to say that we can also correlate this data with other database applications and other data sets to determine certain characteristics of these infestations. So we now know where these populations are. Let's start painting a picture of certain characteristics. So how much water are they using over time? what is their density? We know where they are, but how dense are they? This is very important information for the guys on the ground that are doing planning. And then also cost-benefit analysis. So we know the extent and coverage across the landscape of these certain populations. How much is it going to cost to clear them over time? And also, what sort of profits can we gain from the water savings that we get back after clearing the invasives? And that's just my references, and I thank you guys very much for listening. Thank you.
Hi everyone, my name is Thandakas Khosana. I am a master's student at Stellenbosch University. My main supervisor for the project is Dr. Alana Rebello from the Agricultural Research Council. My co-supervisor is Prof. Karen Esler from Stellenbosch University. So I'm here to just present preliminary results for the Umzimvubu catchment. So this talk will be titled Detecting Woody Invasive Alien Plants Using Sentinel-2 Imagery in the Umzimvubu Eastern Cape. Okay. So what are invasive alien plants? Invasive alien plants are plants that grow out of their native range that have been intentionally or unintentionally introduced mainly by human behavior. So they have negative impacts on the ecosystem. They decrease biodiversity, impose risks to water security, and also affect economies of many countries. In South Africa, woody invasive alien plants such as gums, wattles, pines have been shown to significantly decrease surface runoff, and billions of rands are actually being spent in clearing efforts. Between the years 1998 and 2020, 7.1 billion rand was spent in clearing efforts. Clearing has been shown to be beneficial. However, it is hindered by high costs and lack of knowledge on the distribution and severity of invasions in South Africa. I won't spend time on this because Liam already went through it, but basically my master's project falls under the bigger project. And yeah, the methods are quite standard for this. All right, so my study area is the Umzimvubu catchment. The catchment is composed of 5 tertiary catchments. It's actually quite a big area. It's about 19,852 square kilometers, and the Umzimvubu River is approximately 400 kilometers in length. This river system is one of the least constructed ones in South Africa, meaning that it still preserves its natural flow regime. So my stakeholder workshop was in person. We held it on the 22nd of February 2023 at the Umzimvubu Catchment Partnership quarterly meeting. So the UCP is basically a program where a group of organizations linked up with the main goal of preserving the Umzimvubu catchment. So they do so by engaging with local communities to practice to improve land management practices, and also they are involved in alien clearing in the catchment. So the aims of the workshop were basically to get more information on the problematic invasive alien plants in the catchment, and also to learn more about access to dense infestations to collect our training data. All right, so the field work for the Umzimvubu took place for 3 weeks. We started on the 19th of May and ended on the 6th of June, 2023. So we used road networks to collect ground truthing data. So these were the different land use land cover types approved by our stakeholders. So we collected a number of metadata, which is land use land cover type, coordinates, direction, distance, and for our invasive alien plants, we looked at age, we estimated age, and also density. So after every day, we took our training data and processed it on ArcGIS Pro, and for the Umzimvubu catchment, I think we had about 4,900 points in total. And then all these training data are uploaded on iNaturalist. So data analysis, I used Sentinel-2 for my classification. Sentinel-2 has 13 spectral bands, and then they have the red edge vegetation bands, which are used to improve invasive alien plant detection. And we know that spectral vegetation indices and bands also promote high accuracies in multispectral sensors. Hence, I used this table actually shows the features that I use, which are bands and indices for Sentinel-2, and I also infused that with Sentinel-1 to get proper accuracy. Cool. All right, and then I used Sentinel-2 imagery from May 2023, which was like a couple of days before my field trip. And for this, we did validation, 70% for training and 30% for validation, and then I did an overall accuracy assessment. So after the stakeholder workshops, we saw that there were 3 main species of wattle in the catchment: black wattle, silver wattle, and green wattle. And we've been told by locals that they favor black wattle more because they use it for firewood and charcoal, and then the rest are deemed useless. So just during the field, to determine the different types of wattles, we actually went up to the stands, looked at the leaf and everything, just to be sure that we're looking at the correct type. All right, so these are fieldwork results. So silver wattle was the main dominant species in the catchment. We found it in grasslands and riparian zones. And then maize was the dominant land use land cover type. It was literally everywhere. We had so much maize. And then there were pine plantations on the south of the catchment. And then there were also old non-active gum plantations, mostly from Sapi. And we noticed that communities actually chopped them down, so most of them grew from coppice. And then they also had very beautiful wetlands. All right, so this is the overall classification from the Umzimvubu. The most dominant vegetation type is grassland, followed by dryland agriculture and indigenous bush. As you can see in the center, that's where we have black wattle dominating. And right on the south, that's where you have pine in red and our gum plantation. And these are the results for my pine and gums. And as you can see, the accuracy is quite good. The red being the gum, the pine, sorry, and the orange is the gum plantation. And then this is silver wattle. I would say that the classification probably mixed it with black wattle a bit. As you can see, there are some that dark purple is black wattle, and then the light purple is silver wattle, so there was a bit of mixing there. However, I think we're quite happy with this because it matched exactly what we saw in the field. And then this is black wattle. So black wattle is the dark purple, and then it's surrounded by indigenous bush. All right. And then I had very low points for green wattle. Hence, I think it's one of the reasons why the algorithm couldn't classify it properly. So as you can see, it's very mixed with gums, silver, and everything else. So closing remarks, I could say that Sentinel-2 proved to be able to discriminate between different wattle species, especially silver and black. However, in the cases of silver, it was a bit mixed with black wattle. So these results show the maps of the different wattle species, and I believe these maps could be used to assist local people and organizations with strategic management. So further analysis like phenology and time series could be used to improve our results. And these are my references. I would like to thank the following organizations and my team. Thank you.
Thank you very much. Since we're running late, we are not going to take any questions, but our panel will be available during lunch to take and address any of the questions that you've posted up onto the poll. Thank you very much. Thank you, guys. That was really, really excellent, and thank you for sticking to my time limits. Appreciate it. Thank you, audience. Please bear with us. I hand over to ma'am.
Thank you so much. Thank you, ladies and gentlemen. This concludes our second session for the day. And with that being said, lunch is prepared for all of us. I would like to request Major Finger, our counterintelligence officer from the South African Air Force, to please hand over the gifts to the speakers, and our moderator. Thank you so much, Ms. Tanisha Chetty, as our moderator for the day. The speakers, if you can please step forward kindly to receive your gifts as our token of gratitude.
We're a group, we're trying some team effort stuff.
Ladies and gentlemen, you may please proceed to the foyer for our lunch break. Time is now 14:35. I would kindly request that we be back here at 15:05. Thank you.